In this video, I'm going to talk about the addition rules of probability. And these rules apply to questions like, what is the probability of event A or event B? And in these types of questions, students often notice that we can add those probabilities together to find the answer. And I'll give you an example. So let's say we consider the experiment of rolling a die. If we write out that sample space, we can have a 1, 2, 3, 4, 5, or 6. And let's say I ask the probability of rolling a 1 or an even number. So I could do this in a couple of ways. I could just look at this all together and kind of go through the sample space and ask myself, okay, is this a 1 or an even number, and then count it. So I've got a 1, so I'm going to count that. 2 is even, I count that. 4 is even, and 6 is even. So then I look and I say, oh, I have 4 that satisfy these conditions out of 6 total. So the probability of rolling a 1 or an even number is 4 out of 6, and we could reduce that. I'm just going to leave it 4 out of 6. The other way that you could look at this is you could look at these events separately. You could say, okay, well, how many outcomes represent rolling a 1? Well, there's only one, and that's the 1. So 1 out of 6 chance that you roll a 1. And then I could look at how many different times can I get an even number? Well, 2 is even, 4 is even, 6 is even. So 3 out of 6 represent an even number. I can just add those together. 1 6 plus 3 6 is 4 6, and that's the same answer that I got the first time. So 2 different ways to look at the problem. And this works really well when there's situations where there are no common elements for the events. So for example, it's impossible to roll a 1 and an even number at the same time. And events like this that have no common elements are considered mutually exclusive events. So they cannot happen at the same time. And so I'm just going to label these. These are what we call mutually exclusive events. Rolling a 1 or an even number. And what I did here, if you look at the box, so there's a couple of addition rules here. And addition rule 1 says for mutually exclusive events, so that would be like this situation where rolling a 1 and an even number, those can't happen at the same time. If you want to find the probability of A or B, all you have to do is take the probability of the one plus the probability of the other. And that's exactly what I did here. So if I want to know the probability of rolling a 1 or an even number, all I have to do is find the probability of rolling a 1 and add that to the probability of rolling an even number, and that'll give me the answer. And so when there are common elements, we have to be careful about double counting. So let's look at an example where we don't have mutually exclusive events and we have to be careful about that double counting. Let's consider the problem. What is the probability of rolling a number less than 4 or an even number? Okay, so the first thing to ask yourself is it possible to have a number that's less than 4 and even at the same time? And there is. So the number 2 is less than 4 and even. And so this is a situation, these are not mutually exclusive events. And these are the type of events, this is the type of problem where you do have to be careful about double counting. So let me show you what I mean. So you could approach this problem and say, okay, I'm just going to count all of the outcomes that apply here. So if a number is less than 4, I'm going to count it. If it's even, I count it. So I'm going to count 1 because that's less than 4. 2 is less than 4 and it's also even, so I count it. I don't count it twice, I just count it once. 3 is less than 4, so I count it. 4 is not less than 4, so I wouldn't count it for that, but it is an even number, so I'm going to count it. 5 is not less than 4, it's not even. 6 is even, so I count it. So if I go through carefully, I can see that there are 1, 2, 3, 4, 5 different outcomes that match either one of these statements or both. And so there's a 5/6 chance of getting a number less than 4 or even. Let's look at the addition rule that we were talking about before. So if I use the addition rule, so now I'm going to bring out my different colors. And if I just look at numbers less than 4, let's identify those. So numbers that are less than 4 are 1, 2, and 3. So there are 3 out of 6 that are less than 4. And then if I look at numbers that are even, there are 2 is even, 4 is even, and 6 is even. And I'm going to go ahead and just erase these blue dots since we don't want to mix that up with the red. So we've got 2, 4, and 6 that are even. And so notice that the 2 satisfies both these conditions, number less than 4 or even. So I've got 1, 2, 3 of those. Now, if I just use the addition rule that I used with the last example and I added these together, I would get too much because 3, 6 plus 3, 6 is not equal to 5, 6. It's equal to 6, 6. That doesn't work. And so in this situation where you have not mutually exclusive events, you need to use what we call addition rule 2, where it's very similar to the first one. You're going to add the probabilities together, but then you're going to subtract any common element. So probability of A and B, this just stands for common elements between the two. So if I use this formula here, what I can do, so if I want to find the probability of a number less than 4 or even, I can find the probability of a number less than 4 plus the probability of an even number minus the probability of both. So number less than 4 and even. So let's look up here. So I've got my number less than 4. The probability of that happening is 3, 6. The probability of getting an even number is 3, 6. And then the probability of having a number less than 4 and even, well, there's only one of those, and that's 2. So I'm going to say minus 1, 6. And what that does is it makes sure that I'm not double counting, because over here, when I added the 3 and the 3, I ended up counting that 2 twice. So what this formula does is it has us subtract that out so that we don't double count. So then if I add and subtract the numerators, I've got 3 plus 3 is 6, minus 1 is 5, so my answer is 5, 6. And that's the same answer I got in the beginning, just by counting. So let me just back up a second. If we decided not to use the formula at all, like we did in the beginning, and just say, okay, well, there's 1, 2, 3, 4, 5 different numbers that satisfy these conditions, being careful not to just double count that 2 twice, you can also get 5, 6. So keep in mind that with a lot of examples, you can get away with not even using these addition rules and just counting, as long as you're careful not to double count. Okay, so let's jump into an example. Okay, so in example 1A, we're going to consider the experiment where we roll a die one time. So same example that we've been using. So our sample space is 1, 2, 3, 4, 5, and 6. So for A, we want to find the probability of rolling a 4 or a 6. And so the first thing that we want to do is we want to ask ourselves, are these events mutually exclusive? Can they happen at the same time? And they can't. You cannot roll a 4 and a 6 at the same time. So these are mutually exclusive events. What does this mean for us? It means that we don't have to be careful about double counting. We can just go through the list and count all the 4s and all the 6s and add those together. So we can use this first addition rule where we just add the two probabilities together. So the probability of 4 or 6 is just the probability of getting a 4 plus the probability of getting a 6. So the probability of getting a 4 is just 1, 6, because there's one outcome, there's 1, 4, and the probability of rolling a 6 is also 1, 6, because there's 1, 6 in the sample space, and so I can add those together, and when we add fractions, we just keep the denominator the same and add the numerator, so we get 2, 6. And then we can reduce that by dividing both of these by 2 and get an answer of 1/3. So our probability of rolling a 4 or a 6 is 1/3. Keep in mind that we could have done this without even using the formula. I could have just said, okay, well, out of these 6 possibilities, how many are a 4 or a 6? There are 2, and immediately just jumped to 2 6 and reduced it. So that's another option. Okay, so let's look at the second example. So find the probability of rolling an even number or a number less than 5. So probability of even or less than 5. So ask yourself, can I roll a number that satisfies both of these conditions, that's even and less than 5? And the answer is yes. So the number 2, for example, and 4 are both less than 5 and they're both even. So this is an example where the events are not mutually exclusive. So you have a couple of different options here. You could just forget the formula. So you could use addition rule 2, but you could not. You could forget that formula and you could say, okay, well, there are 6 different possibilities when I roll a die. Let's go through the sample space and I'm going to circle all of the options that are either even or less than 5, and I'm just going to be careful not to double count. So 1 is less than 5, 2 is less than 5 and even, 3 is less than 5, 4 is less than 5 and also even, so I circle it. 5 is not less than 5 or even. 6 I'm going to circle because it's even. So the word or means either or is okay. So as long as one of these is present, then we circle it. If both are present, you also circle it. So there are 1, 2, 3, 4, 5 different outcomes that represent either an even number or less than 5 or both. And so we say that the probability is 5, 6. The other thing we could do is we could use the formula. So with the formula, we're going to be careful to use addition rule 2 since we have events that are not mutually exclusive. And so we're going to add the probability of the 1, so the probability of getting an even number, plus the probability of a number being less than 5, minus the probability of both. So this is going to be even and less than 5. So let's look at these different, let's look at these and count how many satisfy these conditions. And so for probability of being even, I'm just going to circle all of the even numbers. So 2, 4, and 6. There are 3 out of 6 outcomes that represent that are even, and there are, let's count the ones that represent numbers less than 5, and so any number less than 5 I'm going to circle. So this is less than 5, 1, 2, 3, and 4. There are 4 out of 6 outcomes that are less than 5. And so notice the 2 and the 4 I ended up circling twice because they fell into both categories. And so I wouldn't want to just add these fractions together because then I'd be double counting the 2 and the 4. And so that's where the formula comes in. It helps us out a little bit. It says, hey, count all of the numbers that are even and less than 5, and you can see those are the ones that we double counted. So there were 2 of those. And so I'm going to subtract out 2. So now I'm going to keep the denominator 6, and I'm just going to add and subtract the numerator. So 3 and 4 is 7, minus 2 is 5, and I got the same answer as what I got in the beginning. And you might be, you might ask yourself, I know I have students ask this question, well, why do we even learn the formulas if I can just count? Well, it's sometimes nice to have different options, and some students really prefer these formulas. So I think this is one of those situations in math where you just have to look at your different options and you have to pick what's right for you. Okay, so next we're going to look at example 2. A restaurant has 3 pieces of apple pie, 5 pieces of pecan pie, and 4 pieces of pumpkin pie in its dessert case. So before I read any more, I'm just going to jot that down. So we have 3 apple, we have 5 pecan, and we have 4 pumpkin. And I'm going to add those all together, and so we have 12 total. If a customer selects at random one kind of pie for dessert, find the probability that it will either be pecan or pumpkin. So we're looking at the question, probability of pecan or pumpkin. Okay, and then it asks, are the events pecan and pumpkin or pumpkin mutually exclusive? So that's actually a good place to start before we do the probability question. Are they mutually exclusive? So you have to ask yourself, can these happen at the same time? So can I pick a piece of pie that's both pumpkin and pecan at the same time? And the answer is no. The pie is either going to be pumpkin, it's either going to be pecan, it can't be both. So these events are mutually exclusive events. That makes it easier for us in terms of doing the probability question because we don't have to be careful about that double counting. So at this point, you could do one of two things. We could use our formula. So that just says for mutually exclusive events, probability of A or B, we just add those probabilities together. So probability of pecan plus the probability of pumpkin. So let's go through our list. If we have 5 pecan pies, the probability of picking pecan is 5 out of 12. And then if there are 4 pumpkin, then the probability of pumpkin is 4 out of 12. And then I add those together, I get 9 out of 12. And then I always ask myself, can I reduce this? And I can. 9 and 12 both have a common factor of 3. So I'm going to divide both of those by 3. And I end up getting 3/4. And so the probability of picking a pecan or pumpkin piece of pie is 3 out of 4. The other thing that you could have done in this case, if you want to, list all these out, is we just could have counted in our list. So there's 5 pumpkin or 5 pecan, 4 pumpkin. That's 9 together. It's 9 out of 12. So which really essentially is just using the formula anyway. So we're just adding those together and no need to worry about double counting because they are mutually exclusive. Okay, so let's do one more example. All right, so in example 3, we have a table. In Patricia's closet, she has the following shorts and skirts. Find the probability, if she grabs a random item, that the item is black or a skirt. Are these mutually exclusive events? Okay, so we're looking at the probability, I'm just going to write this out, of an item being black or a skirt. And before I find that probability, I'm going to answer this question first because that impacts what formula I choose. So are these mutually exclusive events? So is it possible that she picks an item that's black and a skirt? So let's look at the table. It looks like we have a row of black, and that also this 2 right here falls under a black item and a skirt. And so yes, they can happen at the same time. So if it's possible to happen at the same time, we say these are not mutually exclusive. And that means I have to use addition rule 2. So that means I have to find the probability of the one plus the other minus the probability of both happening at the same time. So I'm just going to write that out. So probability of picking a black item plus the probability of picking a skirt minus the probability of picking something that's black and a skirt at the same time. And so the first thing we're going to do is we're going to add up all of these items. So 4 plus 2 is 6, 7, 8, 9. So we've got 9 total items. So my probabilities are all going to be out of 9. And I'm going to look and see how many are black. So I've got the 4 is black and the 2 is black. So it looks like 6 out of 9 are black. And then the skirts are down this row. So we've got 1 plus 2, there's 3 different skirts. So I've got a 3 there. And then I'm going to subtract the black item, the item that's black and a skirt. So that would be like this 2 right here. It falls under skirt and black. And so there are 2 items that are both. So 6 plus 3 is 9, minus 2 is 7, and that's out of 9. So the answer is 7/9. Now let's look at how you would do that without using the formula. So I could say to myself, so I erased all my previous circles, I could say to myself, okay, there's 9 options total, so my answer is going to be out of 9. Let's go through the table and circle any item that falls under being black or a skirt. So this is black, the 4 is black, everything in this row, the 2 is black, and then the skirts are the 1 and then the 2. And then I'm just careful not to double count the 2. So I just say 1 plus 2 is 3, plus 4 is 7, so 7 out of 9 are either a skirt or black. And so notice that was a lot quicker. You know, if it were me, when I do these problems, I prefer just to count like that, and I tend to not use the formula, but the formula is also great. It offers good structure, and so if that resonates well with you, then use the formula. You have two good options to choose from.